Hello, and welcome to Pass the Torque. I'm your host, Katie Caudry. This season, we're learning about all different kinds of topics, from last week's episode about on-orbit servicing to this week's episode about assembly. We have with us today Dale Arney, who's here to talk about all things assembly. Don't forget, you can leave a question in the comments below for a chance to have them answered by Dale later this week. Without further ado, I'll pass it to Dale. Can you tell us about what you do now and your background?
Sure. So I'm a systems architect, and that means that I study how spacecraft work together to accomplish a mission. And I use analysis to determine what are the benefits, the costs, the risks of different options, of different technologies, of different visions for future space missions. Primarily, I've worked human exploration, so a lot of those missions for the moon or Mars are things that I've analyzed and tried to figure out what new technologies we could use and what new ways we could send humans there. Right now, I'm acting as the acting lead for the OSAM National Initiative. OSAM stands for On-Orbit Servicing, Assembly, and Manufacturing, and that's a set of capabilities that allow you to build up and maintain spacecraft that are very large in space or around or on other planets. And the National Initiative is a group of government agencies that are working together to advance those capabilities so that as a government as a whole, we can utilize those capabilities to do all of our different missions. So an architecture for a given mission would include all of the systems that are needed to accomplish that mission from beginning to end. So if you were talking about a human mission to the moon, the architecture would include all the in-space systems, so the transportation systems, the habitats. It would include the landers that go up and down from the surface, and it would include all of the surface infrastructure that's there, like habitats, power systems, rovers, and so on. All of those have to work together to combine to make that mission a reality. And so the system architecture looks at what the functionality of all those different pieces are and how they work together and how they interface with each other to make everything happen that needs to happen in order for the humans to get there and back.
What does it mean to assemble things in space? Can you talk about the past, present, and future of assembly?
The way that you connect something in space depends on what you're trying to do with it. So there are structural connections. Some of those are mechanical, so you'll have like a one piece on one side, another piece on the other side, and you'll click them together and they'll interface with each other and connect. And maybe you have like a pin or something that you push through, and then those two pieces are connected. In some cases you'll have welding, so you'll have these two pieces that come together, and then you'll go around and with a robot arm with a little welder attached to it, weld all that stuff together, and it'll be structurally connected. So assembly is the aggregation of components in space to make a spacecraft. And the reason you would do this is to build systems that you either can't put together on the surface of the Earth and launch all together, but also things that maybe you wouldn't want to. You would want to use smaller launch vehicles or cheaper launch vehicles, and you would launch these pieces up into space separately and then put them all together once you get there to make the fully functional spacecraft. And an assembly is very synergistic with the other pieces of OSAM that I talked about, servicing and manufacturing. So servicing is a lot easier when your spacecraft is already designed to be assembled and disassembled. So if you needed to replace a faulty component or upgrade something, you could more easily disassemble the piece that you want to replace and put a new one in. In terms of manufacturing, assembly allows you the opportunity to actually use the manufactured goods that are created in space and put those into a spacecraft such that you don't have to launch all that stuff from the Earth. Historically, assembly has been done by astronauts, either through EVA, extravehicular activities, where they get out of the spacecraft and they physically put things together. or by flying through rendezvous and proximity operations to dock two or more vehicles together. And so there's a lot of different levels of assembly that we talk about. The first is vehicle level assembly. These are things like the ISS. It took two big, fully functional modules, put them together to make a bigger spacecraft. And they did that over many years and many missions to develop what the ISS is today. Another example that a lot of people don't necessarily think about that I like to point to is the Apollo mission. So in Apollo, they launched the command and service module separate or in the same launch vehicle, but not connected to the lunar module. And once the crew was on their way out to the moon, then the command and service module detached, turned around, and docked with the lander. And in that case, there were two spacecraft. They connected. They became one for that trip to the moon. And that is also at this highest level, vehicle level assembly that we're talking about. In the future, I think assembly is going to be a lot less human-centric, where you have humans either through EVA or through piloting spacecraft actually connecting things, and more with autonomous robotic assembly, where you have robotic capability in space that does all the connections for you. And going forward, I just think that's going to be a lot cheaper, a lot faster, and in many cases a lot more capable than if you wanted the human to do it. So when Station was assembled, the astronauts basically got out and connected things together. The shuttle also had the Canada arm, which is a really big manipulator that could move components into place. With something like OSAM-1, where the assembly that's going on there is smaller, lower level, where you have a communications antenna being assembled, the robotic arm is significantly smaller, first of all, and it does all of the assembly there. Some of it is automated, some of it is teleoperated, but it doesn't require a human in the loop, which for Station that was maybe acceptable because you had a lot of humans available to do the assembly, and it was pretty complex. With OSAM-1, you don't have the humans available, and if you designed it such that it needed humans, it would be so much more expensive that it would be difficult to make that work going forward. Kind of make a business case out of it.
Why is assembly important? What are its benefits, and what are some future applications?
Yeah, so assembly specifically and OSAM in general is a revolutionary new way of operating in space. It can really change the paradigm and change how humans use space going forward. And right now in the national initiative, we are looking at what the value proposition is for OSAM and assembly more specifically. And that value proposition has different meaning for different use cases. So a really large telescope versus a persistent platform versus a lunar surface infrastructure. Each of those use cases have different values, and then each of the stakeholders that would use that would also have different definition of value. So we work across civil, national security, and commercial space in the OSAM National Initiative. So each of those stakeholders have a kind of a different reason why they want to use this capability, and so their value is different. And so some of the uses for OSAM capabilities, there are a lot of near-term current vision. So think ISS, that's something that we're using right now. But then there's also a lot of really far-out visionary use cases that can really change how we operate in space. The ISS is an excellent demonstration of OSAM capabilities, but it's also an excellent demonstrator of new OSAM capabilities that we're going to use going forward. And some of my favorite kind of future visionary use cases, a propellant depot. These are gas stations in space that you can go and fill up before you go on your interplanetary mission. and this allows you to do Mars missions, moon missions, a lot easier and a lot cheaper because you don't need to take all the propellant with you up on the initial launch of the system. You can launch up there, fuel up, and go. Very similar to how we operate terrestrial. Another one, persistent platform, allows you to plug and play payloads like instruments or experiments, and then upgrade and replace components over time so that the platform evolves. The Large Space Telescope, like I said, allows you to find Earth-like exoplanets out there in the galaxy. And then finally, surface infrastructure for the moon or Mars or any place that humans would want to go. This set of capabilities allows you to maintain, reuse, and grow that surface infrastructure over time in order to support human exploration today and then also make it sustainable heading into the future.
How are different NASA centers collaborating on assembly? What role does the private sector play?
Yeah, so the NASA centers work together quite a bit on this. We work with basically all the centers in OSAM in general, but in assembly as well, because OSAM is kind of an integrated set of capabilities. It's not just assembly, it's not just servicing and just manufacturing. They all work together to help advance that set of capabilities. So all the centers really contribute: Langley, Goddard, Marshall, JPL, all of them. And we work together to try and make these capabilities go forward so that these kind of new paradigms can be implemented in missions. And also, kind of at a lower level, OSAM is very multidisciplinary, so we bring together skills like systems analysis and architecting, structures and mechanisms, autonomy, modeling and simulation. Bring them all together to make a system that works together. And we collaborate not just within NASA, but also outside with other government agencies through the OSAM National Initiative, particularly, but also academia and industry. They're all developing kind of fundamental capabilities that we can then leverage and integrate together into the new systems that we're looking to provide.
Can you describe the A part of the OSAM-1 mission?
So the A part of the OSAM-1 mission is a demonstration called SPIDER by Maxar, and SPIDER stands for Space Infrastructure Dexterous Robot. And so after the refueling of Landsat 7, a separate robot arm associated with SPIDER is going to robotically assemble a functioning communications antenna. So the boom that the antenna sits on and all the antenna pieces are kind of mounted to the side, disassembled. Then the robot arm will deploy the boom and start attaching the pieces of the array to the end of that boom and create a functioning communications antenna. This will be kind of the first time that's ever been done. Parts of that antenna were developed at Langley, particularly the joint between the boom and the antenna itself, or the dish itself. And so the idea here is that you would be able to launch with something that's not put together, that's maybe really efficiently packaged, and then instead of having to deploy it, you would have a robotic capability there to assemble the pieces that you would need. And the demonstrations across all the aspects of these OSAM-1 missions are helpful to each of the other three areas: the servicing, assembly, and manufacturing capabilities going forward. Because you could imagine this antenna that's being assembled maybe uses manufactured products. Maybe it's up there to fix a spacecraft that didn't deploy its antenna, or its antenna somehow broke or something like that. So this idea of being able to assemble an antenna is pretty powerful going forward. Even though it may look like a small step, it's a step in the right direction.
Can you tell us about TALISMAN and other assembly work being carried out at Langley Research Center?
Sure. So TALISMAN is what they call a tendon-actuated manipulator system, and it's a long-reach manipulator kind of on the order of the arm that's on space station, and it uses instead of like rigid beams and joints with motors in them to move the arm, it uses tendons, so cables that they pull one way or the other to get the arm to move side to side. And so that's being developed at Langley in conjunction with some other technology that is very similar. The LSMS, which is the lightweight surface manipulator system, is a similarly tendon actuated. We used to call it the lunar crane because it's very functionally similar to a lot of construction cranes that you have nowadays, where because you're in a gravity field, you only need one tendon on one side to pull it up, and then gravity will pull it back down. But it allows you to do things like offload payloads from the surface, but it's also a manipulator in itself, so you can move things around once they're on the surface. It can be used to help with construction or excavation or anything like that. So this technology is very similar. One is an in-space application, one is a terrestrial application. We're kind of combining all of these capabilities to try and develop systems level solutions for OSAM use cases going forward, so that we can really take advantage of this kind of new paradigm of operating in space and create end-to-end systems with coherent value proposition and everything that goes with it.
What NASA mission are you most excited about?
So I really want to see what sustainable human exploration looks like. My goal is for humanity to become a spacefaring civilization, which means the economic sphere of influence extends out into space. We're using the vast resources of space to help life here on Earth and in space, and it's affordable for people to live and work off of the planet Earth. And this view is kind of built on what I call the four pillars of spacefaring civilization. And those pillars are low-cost access to space, so utilizing low-cost launch vehicles and other systems. Refueling, being able to stop at the gas station and fill up on your way to somewhere. OSAM, which we've talked extensively about today, so that you can build large things, maintain them, reuse them. And then the last one is in situ resource utilization, so being able to live off the land, extract materials from the moon, Mars, asteroids, and use that for propellant or construction materials. And I really want to see how we accomplish these things in these four different areas, and how we move in that direction of a spacefaring civilization. And so I'm excited to see how OSAM can help us move towards that vision. And the agency, for under Artemis, they want to do the first woman and next man in 2024, and then after that, sustainable lunar exploration. I really want to see what that sustainable lunar exploration looks like.
What is the best part of your job?
So my favorite part about this job is just creating the future where humanity is a spacefaring civilization. So when I was a kid, I used to draw little pictures of moon colonies or whatever on my notebooks and stuff. And now it feels like I'm doing that same thing, but for real. And I'm helping us chart a path towards this vision that I would really like to see. What could and should a spacefaring human civilization look like? I get to actually contribute to that in real life. It's not just a doodle on my 8th grade math notebook. So, that's what excites me every time I dive into a new challenge where we have a mission that I'm not sure how we're going to do it. There's so many different ways, and I get to kind of use my system architecture skills to look at the different options and see how these visions could look going forward, and kind of pick one, and it has some meaning in terms of where we're going as a civilization. So kind of big picture, but it just really excites me to do that every day.
What do you like to do for fun outside of NASA?
So outside of work, like most nerdy kids, I like video games and computers. Last year or the year before, I built my own gaming computer that I also use to try and learn like some machine learning and deep learning type stuff, because all that interests me personally, and I do that outside of work. I also do a lot of woodworking. I like being able to make something, so being able to kind of think of it in my head, sketch it out, and then go down in the shop and make it and figure out what the best way to make it is, and then put it all together and then see the final product that we get to use. It's very, very exciting to me. And then lately, since this COVID pandemic, I've been learning how to teach kindergarten and first grade and preschool, because that's kind of taken over our lives. So when my wife is working, I'm with the kids, trying to teach phonics and how to add and stuff like that. And then while I'm working, she's doing that. So it's been a huge learning experience of something that I didn't really think I would ever have to do, but here we are, and I'm trying to figure it out and make the best of it.
Thanks so much, Dale. And now it's your turn to ask a question. Go ahead and drop a question in the comments below about on-orbit assembly for a chance to have them answered by Dale later this week. Don't forget to join us next week to learn about on-orbit manufacturing. Thanks so much for tuning in, and we'll see you next time.
I built this desk, which is mine, and that desk, which is my wife's, in here so that we could each use it. I also built this shelving unit a couple years ago to house all of our stuff. I also built this kitchen table with storage benches. I did that over Christmas so we could have some storage space for various things in the kitchen here. And since the school's closed and the COVID pandemic has raged on, I've had to learn how to teach kindergarten and preschool and first grade. So here you can see our word wall. This is the dining room, or maybe formerly the dining room. It's now the place where the kids do school. Here are their desks that came from the office. This was originally a big L-shaped desk, and we took it apart and made it into two smaller desks for the kids so that they can do their schoolwork, and we'll see how much longer all this has to show up.